Water formation on the Moon demonstrated for the first time. A cross-disciplinary study has shown chemical, physical, and material evidence for water formation on the Moon. Two teams from the University of Hawaii at Manoa collaborated on the project, physical chemists at the Manoa Department of Chemistry's W.M. Keck Research Laboratory in Astrochemistry and planetary scientists at the Hawaii Institute of Geophysics and Planetology HIGP. Although recent discoveries by orbiting spacecraft such as the Lunar Prospector and the Hard Lander Lunar Crater Observation and Sensing Satellite suggest the existence of water ice at the poles the Moon, the origin of this water has remained uncertain. Lunar water represents one of the key requirements for permanent colonization of the Moon as a feedstock for fuel and energy generation, hydrogen, oxygen, and also as drinking water. The breakthrough research is outlined in Entangling the Formation and Liberation of Water in the Lunar Regolith, authored by Manoa postdoctoral fellow Cheng Zhu and colleagues in the Proceedings of the National Academy of Sciences. Chemistry professor Ralph I. Kaiser and HIGP's Jeffrey Gillis Davis designed the experiments to test the synergy between hydrogen protons from solar wind, lunar minerals, and micrometeorite impacts. Zhu irradiated samples of olivine, a dry mineral that serves as a surrogate of lunar material, with deuterium ions as a proxy for solar wind protons. Deuterium irradiated only, experiments did not reveal any trace of water formation, even after increasing the temperature to lunar mid-latitude daytime temperatures, Zhu explained. But when we warmed the sample, we detected molecular deuterium, suggesting that deuterium, or hydrogen, implanted from the solar wind can be stored in the lunar rock. Kaiser added, therefore, another high-energy source might be necessary to trigger water formation within the Moon's minerals followed by its release as a gas that can be detected. The second set of deuterium irradiation experiments was followed by laser heating to simulate the thermal effects of micrometeorite impacts. A burst of ions with mass-to-charge ratios matching that of singly ionized heavy water was observed in the gas phase during the laser pulses. Water continued to be produced during laser pulses after the temperature was increased, suggesting that the olivine was storing precursors to heavy water that were released by laser heating, said Zhu. To image these processes and interpret the broader impact on the Moon and other bodies, HIGP's Hope Ishii and John Bradley used focused ion beam scanning electron microscopy and transmission electron microscopy in the Advanced Electron Microscopy Center. They observed sub-micrometer-sized surface pits, some partially covered by lids, suggesting that water vapor builds up under the surface in vesicles until they burst, releasing water from lunar silicates upon micrometeorite impact. Overall, this study advances our understanding on the origin of water as detected on the Moon and other airless bodies in our solar system such as Mercury and asteroids and provides, for the first time, a scientifically sound and proven mechanism of water formation, HIGP's Jeffrey Gillis Davis concluded. Giant impact caused difference between Moon's hemispheres. The stark difference between the Moon's heavily cratered far side and the lower-lying open basins of the Earth-facing near side has puzzled scientists for decades. Now, new evidence about the Moon's crust suggests the differences were caused by a wayward dwarf planet colliding with the Moon in the early history of the Solar System. A report on the new research has been published in AGU's Journal of Geophysical Research, Planets. The mystery of the Moon's two faces began in the Apollo era when the first views of its far side revealed the surprising differences. Measurements made by the Gravity Recovery and Interior Laboratory (GRAIL) mission in 2012 filled in more details about the structure of the Moon, including how its crust is thicker and includes an extra layer of material on its far side. There are a number of ideas that have been used to try and explain the Moon's asymmetry. One is that there were once two moons orbiting Earth and they merged in the very early days of the Moon's formation. Another idea is that a large body, perhaps a young dwarf planet, found itself in an orbit around the Sun that put it on a collision course with the Moon. This latter giant impact idea would have happened somewhat later than a merging moon scenario and after the Moon had formed a solid crust, said Menghua Zhu of the Space Science Institute at Macau University of Science and Technology and lead author of the new study. Signs of such an impact should be visible in the structure of the lunar crust today. The detailed gravity data obtained by GRAIL has given new insight into the structure of the lunar crust underneath the surface, Zhu said. The new findings from GRAIL gave Zhu's team of researchers a clearer target to aim for with the computer simulations they used to test different early moon impact scenarios. The study's authors ran 360 computer simulations of giant impacts with the Moon to find out whether such an event millions of years ago could reproduce the crust of today's Moon as detected by GRAIL. They found the best fit for today's asymmetrical Moon is a large body, about 480 miles (780 kilometers) in diameter, smacking into the near side of the Moon at 14,000 miles per hour (22,500 kilometers per hour). That would be the equivalent of an object a bit smaller than the dwarf planet Ceres moving at a speed about 1/4 as fast as the meteor pebbles and sand grains that burn up as shooting stars in Earth's atmosphere. Another good fit for the impact combinations the team modeled as a slightly smaller, 450-mile (720 kilometer) diameter, object hitting at a mildly faster 15,000 miles per hour (24,500 kilometers per hour). Under both these scenarios, the model shows the impact would have thrown up vast amounts of material that would fall back on the Moon's surface, burying the primordial crust on the far side in 3 to 6 miles (5 to 10 kilometers) of debris. That is the added layer of crust detected on the far side by GRAIL, according to Zhu. The new study suggests the impactor was not likely an early second moon of Earth's. Whatever the impactor was, an asteroid or a dwarf planet, it was probably on its own orbit around the Sun when it encountered the Moon, said Zhu. The giant impact model also provides a good explanation for the unexplained differences in isotopes of potassium, phosphorus and rare earth elements like tungsten-182 between the surfaces of the Earth and Moon, the researchers explain. These elements could have come from the giant impact, which would have added that material to the Moon after its formation, according to the study's authors. Our model can thus explain this isotope anomaly in the context of the giant impact scenario of the Moon's origin, the researchers write. The new study not only suggests an answer to ongoing questions about the Moon, but may also provide insight into the structure of other asymmetrical worlds in our solar system like Mars, wrote the researchers. This is a paper that will be very provocative, said Steve Hawk, a professor of planetary geodynamics at Case Western Reserve University and editor-in-chief of the JGR, Planets. Understanding the origin of the differences between the near side and the far side of the Moon is a fundamental issue in lunar science. Indeed, several planets have hemispherical dichotomies, yet for the Moon we have a lot of data to be able to test models and hypotheses with, so the implications of the work could likely be broader than just the Moon.